everyone. In this session, we will learn about PV mini grid distribution panel. What you will learn are basics of distribution panel, components of distribution panel, good and bad distribution panel installation, and protection devices in distribution panel. Let us start with two types of distribution panel, DC and AC. DC distribution panel is the point in which solar charge controllers, battery banks, and battery inverters are connected together. A typical DC distribution panel mainly consists of bus bars as connection points and protection devices to protect the battery banks and cables to SCCs and battery inverters. The panel distributes the converted DC power from solar charge controllers to battery banks and from battery banks to battery inverters at typically 48 volts DC. Next, we will unbox the panel box and learn the components of DC distribution panel. DC distribution panel consists of protection of outgoing cables to battery inverter that protects the outgoing cable against overcurrent or short circuit. DC terminal or bus bar that is interconnection point of battery banks, SCCs, and battery inverters. It aims to bring several devices into a common conductor and is made of solid copper conductor and tin-plated for corrosion protection. Terminal block is also often used for this purpose. Enclosure that houses the protection devices and bus bars. Protection of incoming cables from SCC that serve as additional recurrent or short circuit protection to the SCC and incoming cable to the panel. Grounding bar that provides grounding connection of the box if metal box is used and diverts voltage from surge protection device when overvoltage occurs. There are things to consider when designing a DC distribution panel. First is heat management of the panel. Ambient condition and power losses of the components affect the heat inside the panel. Good heat management is required to avoid the rating of the components caused by overheating. Second is separation between the positive and negative conductors must be maintained to prevent accidental short circuit. The battery banks contain high energy content, hence significant spark may occur. Last but not least, all cables connection should be securely tightened to prevent fire hazards. Next, we will learn by looking in turn at good and bad examples and best practices of distribution panel installation. Let us start with protection devices in distribution panel, that is to protect the cables and battery bank against overcurrent and short circuit. It will disconnect the faulty device or line in case of short circuit and keep the rest of the devices in operation. The picture shows poor component installation. Incoming cables from SCCs and outgoing cables to battery inverter are not equipped with protection devices. This picture shows a better example of panel than previous one because it is equipped with protection devices. However, two inverters are connected into one terminal of 3-pole MCCB. In this case, we need to do the following to fix this. Separate the connection and connect the two inverters into different MCCB. And use DC-rated MCCB as protection device for incoming cable from SCC and outgoing cable to battery inverter. This picture also shows a bad installation because one MCCB is used to protect 3 battery banks. Please remind that combined protection will make the installation lose flexibility. For example, in the case of fault current in one line, the MCCB will trip the entire line instead of tripping only the faulty line. The picture shows a good example of DC distribution panel installation. Battery banks, SCCs, and battery inverter are protected by MCB and MCCB in both positive and negative side. Please remind to replace the cable with correct cross-sectional area. The current carrying capacity of the cable should at least be greater than the maximum possible current going in and out from the battery banks. Now, you should consider these best practices regarding protection devices in DC distribution panel. Only consider protection devices that have proven DC switching capability and are able to accommodate voltage up to the maximum battery voltage. It is recommended to use MCBs than fuses. MCB or MCCB is more sensitive, easy to identify faults, resettable, safer, and provides easy disconnection. Using fuse would require special tool and spare part that is often unavailable in rural areas. Selectivity of the protection devices should be considered to maintain the MCB that protects battery bank to be the last device to treat in case of fault. The current capability of the protection devices and cables should consider the rating factor in case of high ambient temperature. It is safe to consider the rating factor at ambient temperature of 45 degrees Celsius. We are back to learn from good and bad examples. The picture shows a bad DC distribution panel installation. In this panel, the enclosure is ungrounded. The enclosure needs to be grounded to ensure that the panel is safe to be touched in any condition. In addition, the picture shows that the panel uses improper way of sealing the enclosure by using sealant that makes the installation semi-permanent. This picture shows a good example of enclosure. It is made from polycarbonate that provides good insulation and properly labeled with electrical shock hazard. If the enclosure is made from metal, make sure that the panel is painted using anti-corrosive paint. So, what make a good enclosure are polycarbonate, polyester, or painted steel material can be used for the enclosure. Panel should have double insulation or protection class 2. The enclosure has multiple layers of insulating material between the internal components and the box surface to protect operator or technician from touch voltage. Additional safety precautions such as label and protection from unauthorized personnel should be provided as the system is running at maximum 56 volts DC that can be dangerous to touch, especially in wet condition. Distribution panel should be properly sized in accordance to required number of SCC, battery inverter, and battery bank to be connected. Let us continue with another bad example of DC distribution panel installation. The picture shows panel with a big insertion at the cable entrance, thus providing entrance for animals. We can see lizard manure that indicates small animal can enter the panel. To fix the mistake of previous panel on big insertion, we need to put cable gland with correct opening according to cable cross-sectional area. Reroute the cable through the cable gland. Please remind to also use the correct color of cable insulation to avoid misinterpretation of the function for each cable type. The picture shows that there is neither electrical wiring diagram nor cables label in this panel. This could lead to some difficulties in operation and maintenance. This picture shows an improvement example from the previous one. Electrical drawing and label of the components are attached. It can help operator, technician, or surveyor to identify the installed components and its wiring. Briefly, the example shown in the picture looks good and neatly installed, except that the installation is too dense. Dense installation may cause some difficulties for measurement and maintenance. To fix the previous example installation, allow bigger space between the components. Adequate distance between components and bigger internal space allow the electrical components to dissipate heat. Still related to distance, this picture shows a bad example in which panel is installed poorly, as distance between positive and negative busbar is very close. With such close distance, the risk of short circuit is higher. To fix this, rearrange the positive and negative busbar. The picture shows how to fix previous bad example of panel installation. Not only that the positive and negative busbar have adequate space, but this panel also uses separator to isolate and to minimize the risk of short circuit. This picture shows a bad installation. Several positive cables touch negative busbar and vice versa. This happens because the busbar is arranged vertically. In addition, there is improper cable banding due to vertical busbar arrangement. The picture shows preferable installation with horizontal busbar arrangement. It provides easier cable routing and clear separation and minimizes the risk of short circuit. Now, the picture shows a bad example of fuse installation. Standard fuse case is used without fuse switch disconnector. Using NT or NH type fuse without switch disconnector requires fuse puller and may create arc when disconnecting. The picture shows the recommended installation. Fuse switch disconnector is used. It provides protection, safety, as well as allows easy fuse replacement. In addition to using fuse switch disconnector, we must consider the following. Conduct inspection to regularly monitor the fuse's condition. Measurement is needed when there is any burning sign. Electrical fault must be located and cleared before resetting the MCB or replacing the fuse. Provide spare fuses with similar size and rating at least 20% from the total fuses installed. Let us see another example. The picture shows outgoing line from 4 battery banks in parallel has the same size as individual battery and is not protected by an overcurrent protection device. Unprotected and undersized cable can lead to excessive cable temperature. Always use protection device and proper cross-section of the cable that is calculated based on the possible current passing through, as well as the installation method. The picture shows high temperature due to unprotected and an undersized cable. We are now done identifying a good and bad DC distribution panel installation. However, once in a while, we need to check or maintain the installation. Before performing the maintenance, you should remember the followings. First, ensure the solar charge controllers and battery inverters are disconnected prior disconnecting the battery. And second, because cables connected to the battery bank are always alive, use insulated rubber glove to prevent getting electric shock. Now, we are moving to AC Power Distribution Box or AC PDB. AC distribution panel, or also known as AC power distribution box, is used to divide and distribute the power from battery inverters to feed several loads or feeders. AC distribution panel combines several battery inverters in parallel and connected to distribution grid. Let us start unboxing the panel. Enclosure houses the protection devices and bus bars. Bus bar is the interconnection point between battery inverters, grid inverters, and output feeders. Typically, 4 bus bars consisting of 3 lines and 1 neutral are used for 3-phase configuration, while 2 bus bars consisting of 1 line and 1 neutral are used for single-phase configuration. Energy meter acquires the voltage and current from each phase, calculate the power, and accumulate the energy. Current transformer is used as a current input of the energy meter. It measures the current on each phase and converts the current to a lower current that is readable by the energy meter. Timer and contactor control operational hour of the street light. Usually, the street lights operate only for 5 hours. Mini circuit breaker, or MCB, protects the incoming feeders from battery inverters and the outgoing feeders to the grid distribution. Fuse is used to interrupt the voltage measurement from the bus bars in case of sudden short circuit or damaged energy matter. Surge protection device, or SPD, is used to limit voltage in the event of overvoltage and lightning strikes. Earth leakage, circuit breaker, or ELCB prevents human from electrical shock due to dangerous voltage on the metal enclosure. It will trip if there is a mismatch between current flow in line and neutral, or if there is residual current greater than the LCD rating that commonly is 30 mA. Residual current device, or RCD, is also often used for this purpose. Grounding bar provides grounding for the enclosure, surge protection devices, as well as current transformers. After learning about the components in AC distribution panel, let us take a note what to consider when designing AC distribution panel. Enclosure should be safe from touch voltage in case of fault. This could be done by having good grounding of the enclosure or using double insulation panel. Additional safety precautions such as marking and label should be attached to raise awareness that dangerous voltage is existing in the system. Good heat management is required to avoid significant derating of the components. Meters and light indicators should be available on the door and clearly visible. Next, we will learn about protection devices on AC distribution panel, starting with protection coordination. It is important to understand the concept of protection coordination in installing AC distribution panel because protection coordination is used to ensure that the protection devices operate with the necessary reliability. It is also used to disconnect only the faulty line from the system and to avoid unnecessary disconnection of upstream protection device when overload or short circuit occurs. Next on protection devices is the installation. It is recommended to use MCBs than fuses. In case of fault, MCB is reusable and has higher availability in the rural areas compared to the fuse. Protection for the feeders must be specified and installed according to the requirement of the relevant standards that are PUIL 2011 and IEC 60364. Always check that the MCB or fuse rating is higher than the load current and lower than the rating of the protected cable. All devices should be AC rated and has voltage rating equal or greater than the operating voltage, that is 220 volts AC or 380 volts AC. The last step in installing protection devices is to ensure that devices function properly. For that, you can do the following steps. Verify during commissioning that the protection devices function correctly and use proper rating, not underrated. Conduct regular inspection to monitor the fuse's condition. Burnt fuse or tripped MCB should be investigated immediately. If fuses are used, provide a minimum of 20% spare fuses from the total fuses installed, with similar size and rating inside the box. Now, let us look at some examples of protection devices installation. The picture shows a common mistake in protection coordination devices installation. This installation is a bad example because three-phase MCB is used for three different feeders. In the event of fault current, fault in one feeder will unnecessarily disconnect all feeders. This picture shows the good example of MCB installation. One-phase MCB is used to protect individual feeders. This picture shows another mistake in protection devices installation. This is unsafe installation of MCB where it is left free hanging in the panel. MCB should be mounted and protected inside the panel. This picture also shows another mistake. Here, busbar is used to interconnect component. Grounding cable is also used as line cable. We are still looking at the bad example of protection coordination devices installation. Can you spot the mistake? The mistake in this picture is that ELCB is not properly installed. In this example, only neutral cable is connected to ELCB. All the lines and neutral should also be connected to the protection device that is ELCB, as ELCB will compare the total current flowing in line and neutral. Moreover, ELCB or RCD can only be used in the following grounding system: TT, TNS, or TNCS. This picture shows the correct installation of ELCB, that all the lines and neutral are connected to the ELCB. All the lines and neutrals shall be connected to ELCB, as ELCB will compare the total current flowing in line and neutral. Please remember that ELCB or RCD can only be used in the following grounding system: TT, TNS, or TNCS. In this example, voltage measurement is unprotected by protection devices. Do not leave cable connection from the energy meter to the bus bar for voltage measurement unprotected. faulty energy meter or wrong connection may cause overload or short circuit. This picture shows the corrected installation of the previous example. Voltage measurement for energy meter is protected by fuse. In this example, cables are not connected to the surge protection device. Without connection to SPD, the system may not be protected from voltage spike. Induced voltage may occur in all phases. Therefore, all the phases including neutral and ground should be connected to the surge protection device or SPD. This is the last example of protection devices installation. SPD in this example shows red indicator. This means that the SPD needs to be replaced. After learning the best practices of protection devices in AC distribution panel, now let us continue by learning on how to distinguish a good and bad AC distribution panel installation. The picture shows a freestanding AC distribution panel that may lead to instability and cause the panel to fall. The picture shows the panels are mounted on the wall and cables are installed neatly. Panel should have rated at IPX minimum to protect installation from surrounding environment. Extra board in the enclosure is used to protect installation from direct touch. As-built electrical drawing is available on the panel. The picture shows a bad example that improper sealant is used at the cable insertion. Cable glands should be used instead. Cable gland is used to prevent animal entering to the panel. It is preferred to have individual gland for each cable. Ungrounded door may lead to electric shock when there is fault or cable insulation failure. There is no guarantee that the door is conductively connected to the box. Attaching grounding cable to the door reduces the risk of having electrocuted when fault occurs. The picture shows that enclosure, including its door, is well grounded. Panel without drawing and label on the cables and components may cause having incorrect connection. As-built electrical drawing is available on the side to indicate the location and interconnection between components. The picture shows a bad example as there is direct contact of phase cable and neutral bus bar. Insulation may be damaged over time due to the sharp edges and friction. Line cables do not cross the neutral bus bar. Avoid direct contact between cable and bus bar from different lines. Bus bar installation of the phases are too close and there is no separator between bus bar. The picture shows adequate distance between line and neutral bus bars. All the bus bars should be identified with labels and are separated using isolated material to avoid direct contact or accidental short circuit. In this example, the meter doesn't function and the thread line is not connected to the meter. Fuse may be blown. Energy meter is working properly and all lines, as well as neutral, are connected to the meter. Ensure that all the phases and neutral are connected to the energy meter for correct reading. The ratio of the current transformer should match with the input current of the energy meter. The picture shows that the output current is not measured by the panel. Output current is needed to identify the power consumption of the load. Current, voltage, and frequency of the electrical systems are shown on the panel. Voltage and current measurement of the output should at least be installed on the panel to display the power delivered to the loads. The information is useful for the operator or technician to see the instantaneous power as well as to detect faults. Wrong installation color for grounding cable is used for the line phase. Correct color should be used instead. The picture shows that cable is not installed with proper cable shoes. Electrical tape is used as insulation and to fix the MCBs. The picture shows bad example of improper cable connection and insulation. Replace the cable with correct line cable that is not chopped. In this good example, neat installation and proper cable shoes are used. Improper connection may lead to an electric arc. The picture also shows that MCBs are not equipped with labels. The picture shows conductors of two core cables are connected in parallel and not protected individually. This picture shows unnecessary cable length and messy installation that may increase the risk of insulation failure and unnecessary voltage drop. In this good example, cables are neatly wired and routed inside cable tray. Color codes and labels are used to identify phases and components. It is time to check what you have learned. It is quiz time.